Okay, so let us continue the discussion on the PD. So, now we have looked at the different ways to solve this PDs. Now, we are looking at going to look at the uniqueness of the diffusion equation and the other things. So, now when you go to the uniqueness, so what we have already seen the solution and all this, like the solution that we have obtained for this kind of initial value problem. So, these are, I mean, there are general solution for the equation in which let us say for this initial value problem there is an initial condition which is f. So, if it is square and integrable, then this should satisfy that f x square dx less than infinity. So, that is what it is supposed to do. Now, before we establish that any solution in the initial value problem satisfy these things, so we need to have certain information or properties or propositions on this. So, like propositions, let us say we had 4, now 5, we say let f is a function continuous and satisfying this if f is continuous and satisfies minus infinity to f square dx less than infinity, that is, so we can put u x t equals to minus infinity to plus infinity, which is f y dy for x belongs to R and t greater than 0. Then what we have, minus infinity to plus infinity square dx less than infinity for all t greater than 0, and minus infinity to plus infinity del u by del x x t square dx less than infinity for all t greater than 0. So, again one can look at this proof in textbook, but we will continue with the some of the other properties, like let f is continuous and satisfies this this particular equation, then V be any solution of the problem where we define del u by del t equals to del u by del x 2 for x belongs to R. The initial values are f x for x belongs to R, and we have other two condition also here. Then what we can have, then we have minus infinity to plus infinity v x t where dx should be less than f x square dx. So, this is again like, so if you have a solution and then like this, so this again one can prove this. So, similarly we can say that let f is continuous and satisfying that equation, then the problem that which is defined here, let us say A, then the problem which is defined in A has at most one solution. So, this is another important information, and again this is an another theory which one can prove it. Like now we can solve or solving the Dirichlet problem in the unit disk. Okay. So, like let us say we have an uxx plus uyy equals to 0 in D1. This is a 2-dimensional Laplacian, and uxy is hxy for x and y belongs to del D1. What is that? This is x, this is y, this is del D1 and this is D1. So, this is a unit disk in R2. So, D1 is x and y which belongs to R2, where x square plus y square less than 1. So, this is called the unit disk in R2, and h is given a function that is continuous in a neighborhood at the unit circle del D1. Thus, we would like to find a solution u, that is harmonic in D1, that takes the values given in this. So, now first by looking at this radial symmetry of the domain, we can probably express this in polar coordinates r and theta. Then once we define that r and theta, then we can use the separation of variable, and then we can look at the eigenvalue or eigenfunction, and then try to find out the solution. Now, first look at the separation of variables. So, by looking at the symmetry of the domain, so we said that x equals to r cos theta and y equals to r sin theta in polar coordinate. So, now we exploit the linearity of the PD and the boundary conditions given in this particular problem. Let us say A1, given in the problem A1, we superposing simple solution of the problem. The strategy here is to first find a special class of function r and theta and then find the solution. So, we start with the boundary value problem, which is given in A1, and rewriting in r theta, what we get is del 2 v by del r2 plus 1 by r del v by del r 1 by r square del 2 v by del theta 2 equals to 0, where r greater than 0 minus pi theta less than pi, and v1 theta is h cos theta sin theta, where theta again going. So, where we have set v r theta is u r cos theta r sin theta. Now, here this h cos theta sin theta will replace that h cos theta sin theta will denote by g theta, where g also belongs to r and period in 2 pi. So, then what we will write this equation is that del 2 v by del r 2 plus 1 by r del v by del r plus 1 by r square del v by del theta 2 equals to 0, and v 1 theta is g theta, and all the conditions here they will remain there. So, now f is a continuous function, that is C2, and z is also C2, then how we can partial derivative, that we will write r theta is f prime r z theta, where r greater than 0 and theta is minus pi. So, del 2 v by del r 2 would be f double prime r z theta for the same condition, and del 2 v by del theta 2 r theta is f r z double prime theta in this given condition. Now, once we replace back in this r theta system, so what we get, f r z theta plus 1 by r f prime r z theta 1 by r square f r z double theta is 0, where r is greater than 0, theta is. So, now assuming v r theta is non-zero for all values of r and theta, so then we divide by both sides by that, and what we get, that f r plus 1 by r f r plus 1 by r square z double theta by z theta, which is 0. So, here this is dividing by v r theta. Now, this is the condition for which this is valid. Now, here if we multiply both sides by r square, we notice that the equation can be written in such a way that the functions that depends only r on one side and other side on theta. For example, if we multiply this by r square, we get f double prime by r plus r f r by f r, which is minus z double prime theta by z theta, which is lambda. So, here we have got everything separated. Now, that we got two differential equations which lead to minus z theta equals to lambda z theta for theta between pi to minus pi, and we got r square f double prime r plus r f r lambda f r for r greater than 0. Now we can have a requirement for the function g, which is periodic of with the period 2 pi, yields that z of minus pi is z pi and z of prime minus pi is z prime pi. So, in other words, one can assume that z can be extended to a C1 periodic function defined on R with a period of 2 pi. Now, if I put everything, this 2-point boundary value problem, which becomes like minus z double prime double theta equals lambda z theta, z of minus pi equals to z of pi, z prime minus pi equals to z prime pi, where theta goes between minus pi. So, this is what we get. Now, we have an we can have an eigenvalue problem. So, like we can see that function z theta equals to 0 for all values of theta. So, and when it solves, we get and refer to this solution is a trivial solution. but we are interested for the non-trivial solution and the special solution for this boundary value problem. So, we can see that this non-trivial solution depends on value of lambda of the ODE. So, there are certain values of lambda for which has a non-trivial solution, for the rest this boundary value problem will have trivial solution. So, now the value of lambda for which this 2-point boundary value problem which has non-trivial solutions, so that would call the so that say for values of lambda provide non-trivial solution are called the eigenvalues and corresponding function would be eigenfunction. So, now this again one can see this proof and all this, that this is possible, and like if we let us say assuming that 2-point has a non-trivial solution, then lambda has to be. So, if we assume this boundary value problem has non-trivial solution, then lambda has to be 0. So, that is an interesting. Now, how to find out this solution? Basically that lambda 0. Now, we have this equation. So, we get z double theta is 0, which is a general solution is that C1 theta plus C2. Now, if we apply the boundary condition, first boundary condition, what we get C2 equals to pi C2 plus C2. So, which after doing we have z theta is C for all theta. So, in particular if C not equals to 0, that z theta is C for all non-trivial solution. So, this is a solution that we have for all theta, which is non-trivial solution, and that is lambda equals to 0 is an eigenvalue. Now, this one we can say that lambda naught, which is 0. So, we pick the special eigenfunction, that is phi naught theta would be 1 for all theta. So, z naught theta would be a naught for all theta. Now, since lambda naught equals to 0, now we can look for the positive eigenvalues of this solution where lambda greater than 0, then the general solution would be in the form of z theta equals to C1 cos root lambda theta plus C2 sin root lambda theta. So, that is also for all theta that we have. So, we have z prime theta, which is minus C1 root lambda sin root lambda theta plus C2 root lambda cos root lambda theta. Now, once we put this with the boundary condition. So, if we use the boundary conditions, we get C1 cos minus lambda pi plus C2 sin minus lambda pi equals to C1 cos root lambda pi plus C2 sin root lambda pi, and second one C1 root lambda sin minus plus C2 root lambda cos minus lambda pi is minus C1 root lambda sin of root lambda pi plus C2 root lambda cos of root lambda pi. So, here we can divide. So, what we get from here, that 2C2 sin root lambda pi is 0 and 2C1 sin root lambda pi equals to 0. So, essentially sin of root lambda pi is 0. So, root lambda pi is n pi. So, lambda equals to n square for n equals to 1, 2, 3 and so on. So, the eigenvalues would be given as this. So, the positive eigenvalues are, so essentially we can say that lambda n equals to n square. So, the z n theta would be corresponding eigenfunction a n cos n theta plus b n sin n theta for n equals to 1, 2, 3 and so on. Now, if we put these things together in the, then we say that the all these eigenvalues and eigenfunction for these 2-point boundary value problems are given by like lambda n equals to n square, and the corresponding eigenfunction z naught theta is a naught, and z n theta is given by like this, where a n is b n r for corresponding. So, now we have another radial component of that boundary value problem, which was like r double prime r or f prime r equals to n square f r for r greater than 0. So, for case n equals to 0, the equation becomes r plus f prime r is 0 for r greater than 0. So, from here what we get, f r equals to c 1 by r, and f prime r, and f r would be c 1 ln r plus c 2, where r greater than 0. Now, c 1 and c 2 are the constants, and c 1 not equals to 0. So, f is given is not unbounded as r tends to 0 plus. So, we are looking for a c 2 function defined on the closure unit disk d 1. So, we must set c 1 equals to 0. So, the equivalent proposition is that limit r tends to 0 plus f r exists, and for n equals to 0, the f r would be constant. So, now for some constant c equals to 1, if we take for n equals to 0, taking c equals to 1, which will give f naught r is 1 for all r. Now, we can consider other cases where n greater than equals to 1. So, the differential equation becomes r f r minus n square f r is 0. So, here we can use f r as a solution r to the power. So, this is an again second order ODE. So, after doing all this, what we will get is that q equals to plus minus n. So, it will have that f minus n r is r to the power minus n, and f n r is r to the power n for r greater than 0. So, the in boundary condition if we apply, so we take this is the physical solution that we will have. So, we will take this is as the solution. So, finally, what we get that V naught r theta is a naught for all r and theta, V n r theta is r to the power n a n cos n theta plus b n sin n theta, all r and theta, and a n is for n equals to 0, 1, 2, and b n for n equals to 1, 2, 3 are the constants. So, this is what you get. Now, actually these things can be expanded in terms of eigenfunction and all this. So, the other thing which would be interesting to see is that like some sort of an Poisson integral kernel or like. So, now the point here, one important another thing which could be interesting to see is the Poisson integral representation like Poisson integral representation. So, what it says that let z, which is defined in minus pi to pi, be a continuous function that can be extended to a continuous 2 pi periodic function in R, we then have that g theta is less than m for all theta belongs to minus pi to pi, where some positive m is some positive constant. So, here the idea here is that we can use some of these properties of the Poisson kernel and extend this one, some of these solutions with the unit disk, and we can show that u or theta would be minus pi to plus pi p r theta minus xi z xi d xi or g theta. So, this is for r greater than 0, theta belongs to minus pi to pi, and this is for r equals to 1 and theta belongs to minus pi to pi. So, this is another thing which could be also bit of handy, but we will see some example and where the separation of variable or these things we can use. So, the another last point which is important to note here is that we can have differentiation or differentiating under the integral sign. So, how do we do that? Actually, so this is an suppose, let us say, suppose h, which is given like is a C1 function, and the define is that h x t equals to ae02 capital H x t s ds for all x belongs to R, t belongs to R. So, here we assume that the function h del x by h x t s and del t by h x t s are absolutely integrable over a and b. Then h is C1 and its partial derivative are given as del x of h x t is ae02 del x of capital T s ds, and what we can write del t of h x t equals to h x t t plus a2 t del t h xts ds. So, this is again a fundamental theorem of calculus, and this is a sort of an special case of, this is a special case of Leibniz rule, where you can have differentiation under integration. So, that is pretty much sort of an conclude the theoretical aspect of this PDEs. Now, we can see some practical example, and then that would give you an idea how to use all this theoretical discussion that we have so far, and that we will do in the next session.